Like Umberto said, besides integration, I've been in the integration space for 20 years. I am really interested in ARM-based chip technology. So about 4 or 5 years ago, when the Raspberry Pis first came out, I put my first cluster together, Kubernetes cluster, having Kubernetes run on each one of these nodes. Each of these boards is 1 gigabyte of RAM. It works. You can't really run any app on it, so it's just not enough memory to do any serious business. However, you know, these boards nowadays are a little bigger. These are what I use now. It's a Rock Pro board. They still have ARM processors. Has 6-way CPU, 4 gigabyte of RAM, and that's actually stuff that you can use. You can actually run OpenShift on it. So, and I've done so. So I'm running my own OpenShift cluster in my basement using these boards. So interesting things happened. A couple of weeks ago, Amazon launched A1, which is an ARM-based cloud. So they asked me to put OpenShift on it and with my integration application, just so that they could show it off at Red Hat Summit this week. And you can see from the stats that these are not small machines anymore, right? You can have a 16 processor VM with 32 gigabyte of RAM. You can put serious software on these nodes. I said, sure, I can do that. I didn't know if I could because, you know, I usually work on the project side, so I don't use RHEL. I use CentOS, where I'm in total control over what packages I put on. Also, it runs in the cloud, so I'm not sitting next to the board where if stuff doesn't work, I can get my hands on it. But I thought this was an ultimate challenge because, you know, having cloud based on ARM processes is the future, in my opinion. It's a lot less power usage, and it's my contribution to a greener world. So I took this dashboard. It's all the same. The only difference is that here, instead of, you know, you can have an option which which architecture you want to use. This is what I did. So this is the official name for ARM 64. So there's an ARC64 image of RHEL. I built my own OpenShift Origin, which is the project version of Origin, an older version, 3.7, because that's the only RPMs I could find. And I put on it Synthesis. Synthesis is the integration software that I'll be talking about. And Synthesis produces integrations. So integrations are pods that are running on OpenShift itself. So these are containerized applications, if you will, and those are ARM64 architecture as well. I'm going to try to start this video. I'm going to skip it ahead a little bit. So this is the overview of Synthesis running on OpenShift. This is the dashboard of Synthesis. So you see 2 integrations. It's built on connectors. Connectors are Camel components. These are all the connectors that we have available at the moment. There's about 30 of them, so you can connect to like Salesforce or Twitter or whatnot. And building one should be simple. That's the whole idea. Like a business user almost should be able to use existing connections that are previously set up and say, hey, I want to, whenever there's a Twitter mention of me, I want to push that into like a local database. So I'm inserting a SQL query here with a variable called task. The output API of Twitter is different from the input API of the database. So you put a data mapper here, you connect those fields up, and you're actually combining 2 fields into one. So putting the screen name and the content of the message. Then you hit the done button, and you publish it out. So give it a name, and then hit the publish button. Now the publish button, what it does is starts to build this container, right? And it takes about a minute to a minute and a half before this container is actually live, which doesn't sound like a lot of time because it does a lot of work. But it turns out if you are working with building a scenario, it starts to get annoying. You have to wait a minute or two before each change. So that's one of the things we ran into. The other thing we ran into is that it's an open source project, right? So if the community is healthy, you get a lot of collaboration. For this project, it's open source, it's Apache. You can use it, it installs with one command. It's easy to set up, but we don't have a lot of community feedback. So it's a successful project on the product side, so it makes money, but the engineers don't get feedback because we get feedback from the community. The community is the loop that we have. So we need people, we need a certain amount of people that want to use it for free, so that the engineers get feedback. We want engineers to be the owners of the project, right? And not just the project managers. The product managers telling us what to do. There should be like a balance between the two. So we stepped back and said, well, let's see if I can go to the next slide here.
Put it in full screen.
Full screen. That's not the next slide. There we go. We said, what are we doing here, right? We have this UI that's building images, and basically what we do with the underlying project is Camel. And Camel is a very healthy open source project. It's been around for over 10 years. It had tons of contributions, and it's still a very active community. It's in the top 3 of most active projects on Apache. So why don't these users come to us, is the question. Well, so let's reevaluate, why Apache is successful. Well, it can be deployed to different runtimes. It's based on the so-called enterprise integration patterns, which is, and it supports over 250 components. Components are the connectors. So there is nothing you cannot connect to using Apache, basically, using Camel. And it uses a powerful DSL. And I think in one picture, you have the pattern book on the left. This is the toolbox. These are the connectors, right? And this is the DSL. And we think that the DSL is important for users to understand what's going on. To give you a little bit of an idea of what the DSL is, this is the pattern. Right? These are the patterns that the enterprise pattern book describes. It's implemented like when a file lands for each row in the file, split it out, do some custom transformation to XML, and then drop it on the queue. That's what that is, right? The DSL is sort of like a Unix pipe, right? This whole thing is the integration, those few lines. That's it. And it's appealing to people. It's appealing to developers that they can use it that way. It's very powerful. In terms of if you code it, all the complexity of connecting to a file system, connecting to a queue is hidden from you, right? You just start some kind of main class, Apache main class, And then this is where your DSL is. This is what you have to write. Synthesis, the big UI that I was showing you in the beginning, all it does in the end is write this DSL. That's what it needs to come up with. But it's not obvious to the Camel users, right, that that's going on, because it's this one big container that's being built and dumped onto OpenShift of Kubernetes. So how can we improve this? What we really want to do is have the Camel DSI be native to Kubernetes. OpenShift is really implementation of Kubernetes. So OpenShift is the Red Hat product that does exactly the same thing plus a few more features. This is the scenario that we'll always envision. This is straight onto OpenShift. This is adding Knative to it, which will give it serverless capabilities. So I will first go to scenario 2. So in scenario 2, what we will do is I'm going to go show you right the product. So we're installing something called an operator into our namespace. And then we're going to run this DSL. So on the left side, there's a little DSL that every second is going to log a statement. We're going to run it. It immediately here on this side, this is the OpenShift console. You see it runs a pod, and it logs null because the body is null. So we're going to add a little bit of text to our body here. And you see, you don't have to wait a minute and a half, right? As soon as this little Camel tool thingy senses that this file stamp changes, it's going to push it right here. And it will take, I don't know, a half a second. So the rolling upgrade is in process here. You see the JVM starts, and there you go. There's the logging. So this is a really nice way of developing integration. So now if you have a complex integration that you need to debug and make work, you can iterate over it. Okay. So how did this work? So this is Kubernetes basic, right? I have a service that deploys as a deployment. Deployment is a data structure in Kubernetes, and then depending on that, it creates pods. And the pods is like a pod and a container are very close to each other. So that's where the actual application runs. So I can build all of that. I can build a container, and I can push it into Kubernetes, and then it runs for me. And what Kubernetes then does for me is it loads it onto the physical layer. So these are the actual, physical machines. I don't have to worry about this. Kubernetes worries about it for me. If you have a custom resource, that's the first thing that happened, right? If we think back to the little video. I deployed a custom resource definition onto my namespace. So what does that mean? I'm going to teach Kubernetes about integrations. So I'm going to deploy an integration as a custom resource definition. So if I deploy an integration, a piece of YAML that's called integration, into my namespace, it's going to know what to do with it. So there's an operator here that I've made that the Camel project is making, the Camel K project, that then reconciles, if something happens with the integration, it's going to create deployments and pods. So the developer doesn't need to know anymore. The developer really only cares about the DSL. And then, again, it puts that onto the physical resources. So to recap, this is the IDE where the developer is developing the DSL in. There's a Camel little command line 2 line that you can put in def mode so that every time you save it automatically creates an integration. And this integration custom resource definition is loaded in the Camel K operator it produces running pods. So this reduces the complexity significantly for the end user. And it's fast. The way it really works is that we're not building containers anymore. We figured that piece of DSL is configuration. And so we push that configuration into a config map. Config map is a Kubernetes structure that mounts into the pod. So each time the config map changes, the pod restarts with a new configuration. But the pod doesn't need, the container underneath it doesn't need to be rebuilt. So we can keep existing containers around and just find the right one to run with your configuration. We can quickly look inside the configuration, in the config map, which components are being referenced in the DSL, so therefore we can figure out which container to pick. So this is about, this was about operators, but Java is still big, right? So, and it's slow. It takes about, I don't know, sometimes 10 to 20 seconds to boot up if you have a reasonably sized integration. So how do we get this faster? If you want to scale down to 0, how can you make it go faster? So Graal is something that compiles down Java to a native code. So here there's a little hello world application. All it's going to say is hello, 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 hello world. You can just compile it in Java, but now you can also, with Graal, create a native image of hello world. The compilation takes longer. Like it's doing a lot of things to make this into a native image. And when you execute it, you'll see if you execute the Java, it takes about a, I don't know, 1/10 of a second. But if you execute the native image, it's 9 milliseconds. So that's cool. So that could be one piece of the puzzle. The next piece of the puzzle is Quercus. Quercus has been under development in Red Hat for about 6 months now, and it is, as they say it, a Kubernetes native Java stack tailored to Graal VM or OpenJDK hotspot. So what it does is it looks at more complex Java, not just a hello world, but Java that has like things in it like reflection and CDI, dependency in injection. And it figures out the whole class path and all the classes that it needs at build time, right? And then it can, because it figured this out at the build time, at runtime, it can be much faster. Also, it eliminates as much dead code as possible, and it minimizes runtime dependencies. So if you put Quercus and Graal together, you can go from like, if this is a little REST example, like REST Easy or something, typically it's 140 megabyte in RAM when you start it up. With Quercus, you can bring that down to 74 megabytes. And then if you compile it down to native code with Graal, you're at a 13 megabyte image, right? So you start up and it only consumes 13 megabytes. Here, this is startup time, cold boot, right? This is, I cut it off here, I think, but this is about 10 seconds to start up. With Quercus on OpenJDK, it's about 0.75 seconds, but with GraalVM, it's 0.01 second. Right? So now this becomes interesting. Now this is fast. You can make Java fast, and which is important for us because all of Apache, the 10 years of development is all in, of Apache Camel is all in Java. So we want to reuse that. So let's do a quick video, a quick demo how this actually works. So this is a little JAX-RS app, and it's going to print out the name in a greeting. So we're going to use Quercus here to build a Docker container. So Quercus was run, and a native image is now pushed into the Docker container, and now we run it up, right? So the container starts in 0.006 seconds. In 6 milliseconds, the container starts up, and it's ready to serve. Okay. Oh, I was going to show that the stats, right? What's the memory footprint of this JAX-RS thing? It's 3.5 megabytes. So it's very small. So now it's able to compete with like the Go implementations. So what's serverless again? Serverless computing refers to the concept of building and running applications that do not require server management. It describes a finer-grained deployment model where applications, well, we're not going to do functions, we're doing integrations here, are uploaded to a platform, then executed and scaled, built in response to the exact demand needed at the moment. So basically the thing we're missing right now still is scaling, right? If this integration is not going to be in use, it should be scaled down to 0. So in order to do so, we're going to need Knative. So Knative is a new project by Oracle that we contribute to, and it helps you build, deploy, and manage serverless workloads. So if you want to use this, the build part is interesting. It's very similar to what I showed you before with the operator framework. The second part is that it can scale down your application to 0 using Istio. The Istio framework basically routes all the traffic to your pod through Istio, and so it can hold on to your events while your pod is coming up. So your pod doesn't need to be up. And so there's a whole eventing infrastructure that you will need to comes with Knative. So I'll quickly show you how that works. It doesn't come free. If you can see, these are all the pods for Istio and Knative that are running. All right. Let's run that again. So if you want to do this for 2 or 3 integrations, it's probably overkill because you're spinning up all this infrastructure to make it happen. But if you have hundreds of integration, this is interesting. So the hello world is the thing that is my container that's terminating now here because it was idle for like a minute. So I'm going to go and execute that, send a request into it. So now it's going to start up a new pod, and here's my response. And you see there's a new pod that was spun up, and it's 16 seconds old. So basically, Camel K can use this infrastructure, and the way to do that is it's a little tricky to switch between these videos. To have, again, the Camel K operator. And we're going to use Camel channels, of Knative channels. And so if Knative, the profile is deployed, if an integration comes in, the Camel K operator can either deploy it without Knative, or if the Knative profile is loaded, we'll start it up with Knative. So this way we can switch between like this serverless mode or regular mode. And between our in our DSL, instead of having direct connections, we'll build channels. So the channels are the Knative channels, or the Knative events are going over. So each of these things can go down to 0. All right, some final remarks that operators really remove the complexity for developers to move their integrations into the cloud. With Quercus, Graal, and Knative, you can add serverless to these integrations. And this has already attracted a lot of attention from the Camel community. So Camel K is a sub-project of Camel now, and there's a lot of buzz around it. And so we're getting now a lot of feedback from the community who want to contribute on this technology. And so a lot of the code that used to be in synthesis is now moved out and part of the Camel K project. So it's simpler for us to maintain it. Plus, it's going to give us a huge boost in performance and scalability. So if because if you compile it down to native code, we can host a lot more integrations on the same infrastructure. That's it for me. Here are some links if you want to find out more about Quercus or Apache Camel or Graal.
Thank you very much, Kurt. So we have time for questions.
So I must admit I was kind of surprised to the trajectory of this lecture. I came in with the preconception that you're probably going to talk about OpenWhisk, considering that, well, first of all, Red Hat kind of got Blue Hat a little bit. Can you say something about that? Like, how does it compare to the stack you've built? Is this is it an alternative? Is it something that lives? Well, basically, can you explain the relation of what you've built to OpenWhisk? Thanks.
Yeah, I think the idea is that with operators, like we can target more to what we want to do. We don't want the overhead of OpenWhisk necessarily if we don't need to. So we chose our own path basically. And the interesting thing is that we really want to integrate Quercus, and so we've been working with the Quercus team to have a Camel K like a native version. So that was important for us to have that in the workflow.
one other question related to the scalability. I would assume that this what you presented, and also OpenShift itself, does not interfere, for example, with using like virtual kubelet of, of Azure. If I would have my on-prem Kubernetes cluster and would like to extend it to the endless number of nodes through virtual kubelet, it would not interfere.
It wouldn't interfere with it. No, it works the same way. Yeah, yeah. The whole hybrid cloud thing is what OpenShift is good at, and that's something we want to keep. Yeah.
So when people talk about serverless, oftentimes it's about function as a service, and then there's that traditional recommendation: a function should be short-lived, and sometimes there's a execution limit of 5 minutes or 15 minutes or whatever.
Yeah.
Now let's say I create an integration. Let's pick on the data side. I read from a database all the purchase orders made that day, and then I feed Elasticsearch text database once a day.
Yep.
And I could do that with synthesis, right?
Yeah.
But in case that takes 30 minutes to process, so it's not that short-lived, would be so could I run it on Knative in the serverless fashion that you described at the end?
You should be able to, yeah, yeah. It's specifically designed for that batch processes will only need to run once a day, and then you don't really want to pay for them anymore, right? So,
so it's not a short, it doesn't have that traditional recommendation that it has to be short-lived up to 1 minute, 5 minutes, whatever.
no, no.
So at the beginning, you talked about how Quercus maximizes the dead code elimination. I was wondering if you could talk about that a little more and how it achieves that.
How it achieves that, I don't know. So that part, because it's very, it was, even within the company, it was kind of hush-hush, so we didn't really know much about it. But what it does is it walks all the code paths. It tries to walk all the code paths at the build time. And so then it figures out code that is not used during that time, and it won't put that into your image. And so a lot of code will not be put into the image. That's the whole idea. Yeah. Sorry, I don't have more detail about it.
Okay. Yeah, I have a question about Kubernetes. We know every system has its scalability limits. For Kubernetes, let's say for a single cluster, so what kind of experience do you have dealing with the scalability? For example, the max cluster size may be 100 or several hundred or several thousand or even more. So in your experience, what's the biggest cluster a single Kubernetes cluster may be?
It really depends on how big you make your cluster, right? But at the moment, if you can buy an online subscription for this project or for this product, and basically we limit you at like 10 integrations, so 10 integrations per subscription. But the problem is because it spins up a JVM, it uses a lot of memory. So going forward, we're assuming that we can go to 100 or 1,000 integrations per cluster.
Any more questions? No? Okay, let's thank Kurt again for his presentation.